Hello and welcome to the solutions video for our Unit 8 practice test on mechanical waves. So, our first one, setting up your home theater system, you place speakers in two corners along a wall at a distance of 5.2 meters apart as shown below. Take the speed of sound to be 350 meters per second here. Testing the speakers, you have an output 120 Hz tone in phase. If you stand along wall A, at which of the distances below should you stand from the speaker in the bottom left corner in order to hear destructive interference? So for destructive interference, the path lengths have to be different by 1.5 wavelengths. So we need to figure out what that wavelength is. Well, we have the speed of the wave and we have the frequency. So the wavelength is the ratio. We have 350 meters per second at 120 hertz. So our wavelength is about 2.92 meters. So there is the first bit. 2.92 is the wavelength, but is that the right distance? So if we go 2.92 up, is 2.92 up and 5.2 across the appropriate multiple of the wavelength? Let's find out. So we need the square root of our answer squared plus 5.2 squared. So that's 5.96 meters. Now if we divide that by 2.91 and then all those repeating sixes, that's two wavelengths apart. So that's not going to give us our 2.5. So that answer that is exactly one wavelength is a trap. So the next one, we have 2.92. And this is at the 1.5 wavelength mark, and the other goes an integer number. That's about 4.34 meters. That's not on the list. So our next one that we can check is the 4.62. So if we do the 4.62 meters divided by 2.92, that looks like about 1.6. Now, the square root of 4.62 squared plus 5.2 squared. Okay, that's about 7 meters. We divide that by our 2.92, and that's a 2.38. So our 2.38 and our 1.58, they differ by 0.8. So that one's not lining up either. So our final option is 8.54. So if we come all the way down again, 8.54 divided by 2.91, and then all these sixes, that is almost exactly 3 wavelengths. And if we take our 8.54 squared plus 5.2 squared, it's almost 10. We divide that by our wavelengths. There we go. 3.43 compared to 2.93. Those are the ones where the path length is off by half a wavelength. So to figure out what the wavelength is, figure out how many wavelengths we've gone off the wall for each of these, and find the ones where they differ by half a wavelength. Next up, in a classroom demo, a teacher attaches a speaker that puts out a tone with a frequency of 813 Hz to the end of a string, and then swings it in a circle over his head at a constant speed of 16.5 meters per second. Speed of sound in the classroom is 3.43. as it travels towards you, wavelengths get shorter, frequency gets longer. So then the observed frequency, we have this, we have to figure out whether we have a plus or minus in here. We want to have a higher frequency. That means we need a smaller denominator. That means we're subtracting. So we're going to take our 343 and divide it by 343 minus 16.5. Go all the way down. Okay, so 343 divided by 343 minus 16.5. And our initial frequency is 813 hertz. So we end up with 854. Now here, we want to choose the best information. We're moving one end of the rope like this. The particle motion will be vertical, and the energy transfer is horizontal because it's a transverse wave. The particles move up and down, but the wave moves left to right. Now we want to replace the rope with a new rope the same length that will carry the waves at a higher speed. So if we want it to be a higher speed, we could go for more density, but it's less mass and harder to stretch. So it's lighter but more rigid. That will transmit the waves faster. Now, you're describing frequency and amplitude to your younger sibling using a musician playing a tuba as an example. The frequency would be which note is played, and the amplitude is how loud the note is. This is just understanding our definitions. Watching waves in a pond as they run against the shore, you measure their period to be 4.5 seconds and estimate their wavelength to be 30 meters. What's the speed of the wave? Well, that's wavelength times frequency, but frequency is the reciprocal of the period. So it's not going to be our 135 we get by multiplying. It's going to be 30 divided by 4.5, which is about 60 over 9. So 30 meters divided by 4.5 seconds gives us our 60, or 6.6 repeating, or 6.7 meters per second. Now, a guitar string has a length of 1.2 meters. You find that its second harmonic makes the strongest contribution to the sound the string makes and has a frequency of 256 hertz. The second harmonic on a guitar string is the one where we have a complete wavelength, making our standing wave. So our 1.2 meters is our wavelength. So we have 1.2 meters times 256 hertz. 307 is the only one in the right ballpark. Now you shout to a friend standing 100 meters away. So the particles in the air move short distances, but the energy goes long distances. And a sound wave is an example of a longitudinal wave in which the particles move parallel to the direction in which the wave travels. Now, we tie one end of a 7-meter rope to a doorknob in the house and hold the other end and pull the rope tight. You flick your hand up and back down, taking 0.15 seconds to perform the move, sending a pulse down the rope. You feel the reflected pulse 1.1 seconds later. So the speed of the waves in the rope, they've gone 7 meters and back again. It's gone to the doorknob and then back to your house. Right? So 7 meters plus 7 meters, we've got a distance of 14 meters for that 1.1 second pulse. 14 divided by 1.1 gives us about 12.72 meters per second. Notice if you forget to double the distance for going there and back, you'd get 6.36, which is also here. Now, how long is the pulse you produce in the rope? A pulse is going to be half of the wavelength. The time it taken to produce it was 0.15 seconds. that'll be half the period. So we have the speed of waves in the rope, and we divide it by 0.3. That would be one full period. We only had half the period of 0.15 seconds because we only produced half a wavelength. It was just a pulse. So our wavelength here is 42, but that is only half of it. Let me see here. So V, well, hang on, that's the period. Sorry. Now we wanted to take our V, we would divide it by frequency. So it's the same as multiplying by the period. That is our wavelength, 3.8. And the pulse is half of that. So the length of our pulse is 1.9 meters. Now, an emergency vehicle traveling at 20 meters per second emits a sound at a frequency of 740 hertz while traveling away from you. This time we are adding because it's going away. So we have 340 over 340 plus 20, and this is multiplied by our 740 hertz, or about 699 hertz. So this solves our practice test.